Now we're going to finish classwork 10.3b. Since there are more volunteers, the Spirit Club has decided to appoint another committee member. If they add a treasurer to the list, how many different ways to select the 4 officers are possible? Okay, so we have 4 officers, which is our selection. And then our total is still 6, with Felicia. So if we put that in as a permutation, since officers are distinct positions, then we get 360 ways into your calculator. Okay, now we're gonna write out the possibilities. As you can see, it's easy to miss one. So that's why I'm doing this with you or for you. A, B, C, D. A, B, C, E. A, B, C, F. A, B, D, E. A, B, D, F. A, B, E, F. I believe that's all the A-B combinations. A, C, D, E. A, C, D, F. A, C, E, F. That's all the AC combinations, A, D, E, F. And that completes anything that involves Al. Moving on to the ones that start with B. B, C, D, E, B, C, D, F. B, C, E, F. B, D, E, F. And then our final one, C, D, E, F. Okay, you did it. You survived. Or you just fast forwarded the video. Whatevs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 possibilities. It was less than this one, but this one seemed a lot easier to remember how to get those. How to write them all down, to remember them all. Okay, 15 possibilities. Whew. All right, flip it over. Compare the results you got for each set of numbers in problems 10-134 when roles were determined, as in permutations, like the officers, and when there were no specific roles, as in combinations, like the committees. How did the number of combinations and permutations compare in each situation? Work with your team to develop a conjecture about the mathematical relationship between permutations and combinations chosen from same-sized groups. Find the pattern from 10-134. Okay, so the permutation, parts A and B. Permutation was 60. And the combination that we got was 10 possibilities. Okay, going on to the next permutation for officers when they added for part C, that was 120. And the combination or the committees with those same numbers was 20. And then going to DI and DII, which is at the bottom, what we just did, 360 and 15. We need to figure out what's happening to get from 60 to 10, okay? The operation, we could say minus 50, but it doesn't really feel like it's gonna be minus when we've been dealing with factorials, okay? So What are we dividing by? That's divided by 6. This one is divided by 5. Sorry, 6. And this one is divided by 24. Okay. 6, 6, 24, that's not really like a straight up pattern. But when we did part A and B, we were using N as 5 and R as 3. So N was 5 and R was 3. Then we had 6, 3, and then we had 6, 4. So let's do N was 6, R was 3, and then N was 6, and R was 3. 5 doesn't relate to 6. 3 times 2 is 6. Okay. 3, again, 3 times 2 is 6. Okay, so it looks like it has nothing to do with the N. It has to do with the R because the N changed, but our operation was still the same. So 3 times 2, maybe it should be R times 2. Yikes. That's not the same. I put down the wrong number. My bad. It should be R equals 4, and I just wrote 3. Okay, so if R equals 4, 4 times 2 is not 24. 3 times 2 is 6. 3 times 2 is 6. 4 times 2 is not 24. 4 times 3. Okay, so it might take you a little while to get there, but you may start to notice that, okay, what if I took R and I times it by the numbers preceding it? So like 6 is the same as 3 times 2 times 1. Four is the same, sorry, 24 is the same as 4 times 3 times 2 times 1. You see how it's being times by the next thing. So this was 6 times your R, and you get 24 because we went up 1. So we just times it by the next one, which is kind of like what you were doing with the social media problems in yesterday's classwork. So 3 times 2 times 1, that is 3 factorial. That's 3 factorial. This is 4 factorial. And so you can see that you may not have gotten there without my help, which is why I'm making this video, but you can see that the operation that's happening from the permutation to the combination, since the combination is significantly smaller than the permutation, right? Because when order matters, you're gonna have way more options. Okay, that's why, I mean, phone numbers, order matters. It's not just any number. I can't just do like, oh, if there's a 5 in there, it doesn't matter when I press it on the phone, okay? So if you have, so this is directly related. So to get from the number of permutations to the number of combinations, you would divide by whatever your R is, factorial, and then you get your number of combinations. So test your conjecture by calculating the number of permutations and combinations of 2 items chosen from 6. Okay, so 6p2 is what we're trying to do. So on the calculator, it says 30. If 2 is my R, then I should be dividing by 2 factorial. 30 divided by 2 factorial, well, that's just 2 times 1. So 30 divided by 2 times 1 is just 30 divided by 2, which is 15. That should give me 15. How am I going to check that? Hey, I have a special formula for that too, which you may have noticed when I was showing you how to put permutations into a calculator. So then I would press 6, PRB, and instead of choosing P, I'm going to arrow to the right to select C, which stands for combinations, 2, and then 15, 15. That is correct. So the actual formula for finding a combination, so you don't have to figure out the permutation first, right? We don't want to have to always figure out the permutation and then divide by r factorial, okay? So the formula for permutation is n factorial over n minus r factorial. Take this formula, divide it by r factorial, which would be timesing by 1 over r factorial. Not r squared, my bad. Timesing by 1 over r factorial. And if you took this fraction and you timesed it by this fraction, then you would end up with n factorial, n minus r factorial times r factorial. And that is how the formulas of these two differ. Now you will use your calculator to test the formula you wrote in problem 10-135. Try 4 items chosen from 20. Does your formula work? I believe that you should be able to finish this classwork without me. But why not? I'll just finish it out. Now use your calculator. Okay, so 4 items chosen from 20, and we want to use combinations, the formula for right here, so 20C4. And they want us to use the formula, they said use the calculator, but that was to help you with the formula. So that would be 20 factorial over 20 minus 4 factorial times 4 factorial. That is equal to 20 factorial times 16 factorial times 4 factorial. That doesn't mean 16 times 4. No. These are very, very different things. Okay, it's much, much bigger than that. Okay, so then I could put this into the calculator, which I know you could use the regular combinations formula, but it's important to understand how to use any of these parts and how combinations and permutations actually work. So you're not just punching it into a calculator, you're actually understanding what is really happening and how these formulas were even created. So we could do 20 factorial, PRB, go over to the exclamation point now, we get to try a new one. And then divide that by parentheses, because 16 factorial times 4 factorial needs to happen, and then 20 factorial divides it. So 16 PRB 4 PRB factorial, close that parentheses, you should get 4,845. Let's try the combinations formula just to make sure that that is correct. 20 combination 4, 4,845. Wow, look at you. You know how to do so much. In one state lottery, there are 56 numbers from which a player can choose 6. Okay, this problem is very confusing in the way that it's written, because when you think lottery, you think of lottery ticket. And in a lottery ticket, I think of lottery ticket because I think of Friends. But anyways, in the lottery ticket, it matters what order those numbers are in. But imagine you stop by the gas station and they literally have just like 56 numbers, numbers 1 through 56 or whatever. Okay, and then you can choose 6 different ones. Does it matter which order I choose those 6 different numbers in? No, because I'm going to buy them all at the same time. Okay, does this make sense? There's one number on each ticket, okay, per se. So you have 56 options, you're picking 6 of them. It doesn't matter if I say, oh, give me 1, 2, 3, 4, 5, 6, or oh, give me 6, 5, 4, 3, 2, 1, because they're 6 separate entities. I'm choosing the order that I choose them in when I purchase them. Does not matter. I don't know if that makes the problem more complicated or easier, my explanation right there, but let me just tell you, the order does not matter in this particular problem, meaning we're going to use a combination. Does the order matter? No. Because you're going to buy them at the same time. At the same time. Find the number of possible combinations for a set of 6 winning lottery numbers. Okay, so I'm guessing that they'll be like, oh, if you have these 6 numbers, then you win. Again, I guess the order doesn't matter because they're separate tickets. It's a little confusing, whatever. They want us to find out what is 56 combination 6. That's the point. Holy cow. Okay, we got a lot going on there. 3, 2, 4, 6, 8, 4, 3, 6. 32 million. What is the probability of selecting the 6 winning numbers? Well, there's only one way you would select the 6 winning numbers if you got all 6 of them and they were all 6 correct. There's only one way for that to happen. So, one way, in how many ways could you have chosen 6 lottery numbers? 32,468,436. Oop, 4, 6, 8. So the probability of selecting the 6 winning numbers is 1 out of 32,468,436. And kids, this is why we don't do the lotto.